Today we are going to be having a look at some analog component video. So we'll have a look at some of the theory behind it, some of the specifications, and then later on we'll get out some equipment and do some demonstrations and experiments and what have you. Now, as with most of my videos, we're basically just going to be talking about the purely analog days, just for historical curiosity, so I wouldn't necessarily recommend following this if you're doing any contemporary production work. Now, the thing that inspired me to make this video is something that I came across some time ago when I was researching a different video where somebody with an interest in AV has come back from the scrapyard with something like this under one arm. Now, it doesn't matter exactly what, but when they get it back home and have a look at it, despite it being bristling with connections and looking all professional, all of the connections on here are actually composite. Like, what gives? Where's the more professional S-video and component video connections? So that's one of the things that we will cover in this video. We'll talk about where these various different types of connections actually fit into the professional workflow.
Component video comes in more forms than you might expect. So for example, the common SCART connection of course has an RGB mode, which you could argue to be component separated video, because it is, even though that terminology isn't generally accepted. And you will also find RGB in the professional space on BNC connections like this. And sometimes you might find a fourth connection with this, and this is going to be the sync, because the sync is often not carried on the RGB channels themselves, although there is this thing called sync on green, which is pretty much standard these days. But of course the main type of component video is more likely to be carried on cables like this. This is the YPbPr variety. And the deal is that you have a luminance channel, which is generally carried on the green cable. Now this is a black and white version of the picture. Then you have two color difference signals, so the blue difference and red difference. And the idea is that you don't need the green channel because you can extrapolate it from these three. And you will also find that same type of interface in the professional environment, where it's generally going to be on BNC connections, and occasionally we'll find a separate sync connection, although sync is pretty much standard on this type of interface. If this is being used, it might be doing something else, fudging the timings or something. So anyway, why would you use component video over composite? Well, we talked about that back in video number 9. Now the main problem with composite is that when you combine the colors, all the color components into a single cable like this in the analog domain, of course you get luminance, chrominance crosstalk, and you basically can't ever really fully separate them. So there's definitely a quality advantage in using component video. But the other benefit is that when you're running this through some piece of equipment which needs to manipulate the image, that is going to require it to be in component form. So for example, if it's manipulating in the color domain, it will want RGB, and if it's manipulating in the monochrome domain, it's going to want YPbPr. Now that's true if it's some particularly ancient piece of equipment. However, modern equipment generally is going to accept either at the input, and it's going to convert internally to whatever it wants. But anyway, the next question is, how does this component video actually work?
This slide here is frequently referenced whenever this question comes up. And it is actually quite helpful because it tells us how we get from RGB to YPbPr. Of course, that's this type of connection here, which most people will be familiar with. But it is also a little bit misleading because of how they've actually presented this information. Now they start off here by saying how to convert from this RGB to YBY, RY. Now the apostrophes here mean that we're talking about gamma corrected inputs and gamma corrected outputs. I wouldn't get too concerned with that for the time being. Now we're going to be focusing on this table here, which is just the standard definition table. So high definition is not really the kind of thing I get too much into on this channel. So first of all, the luminance. Now the luminance is just a weighted sum of the R, G and B inputs, mostly green, a bit of red and less blue. And this is in accordance with human perception of chrominance. And these numbers are of course all adding up to 1. Now next up we have our two color difference signals, starting off with the R minus Y. And this is calculated from basically taking the remainder of the red, so 1 minus 0.299 equals 0.701, minus the other colors, and then we do the same for blue. So we take the remainder of the blue, which is 1 minus 0.114, we get 0.886, minus the other colors. And of course those add up to 1, those add up to 1, these add up to 1, and this is really the beauty of this bit of math here. It's a good way to understand component video. I don't know if it's an actual standard or not. Certainly Tektronix haven't actually listed any actual formal standard here, so I don't really know what they mean by commonly used. Might they be referring to the component separated inputs on this waveform monitor? It looks like it's possible. So we've got a Y input, we've got a B minus Y, and we've got an R minus Y. It does certainly look like what we were just talking about. No. So the input on that piece of equipment is actually this one down here, this YPbPr, of course the same thing that you would find on consumer equipment. So there is an interesting question here of why do we have another standard down here when we've already defined something that looks pretty nice up here? Because, as I say, this the math here is just really nice. If you're thinking about converting from RGB to components, this is just really straightforward, and there's no scaling going on here. So, you know, assuming that there's any loss in a scaling mechanism, if this were a standard for component video, you would always have a perfect conversion from component to RGB and vice versa. So, yeah, so why do we need all this down here? Well, if we look here at the actual ranges involved, so for the luminance here, we have a nice 700 millivolts peak to peak, just for the luminance itself. I'm not talking about the sync component. But then when we get down to the color difference signals, we end up with some different voltages. So we have, for R minus Y, we have 0.98, and then we have 1.24 peak to peak. Now the problem is that if we're trying to digitize these signals, let's say we're trying to fit them into an 8-bit register, which would go 0 to 255, and we've got some kind of circuitry which does that. When we come to digitizing the color difference signals, we have a bigger range, so all of a sudden we need 9-bit registers to store this, this bit information, and that's just a little bit awkward. And you could end up with the same problem with an analog signal path as well. Let's say you've got some components which only have a dynamic range of this, and then you're trying to shove this through it, and it's not really going to work too well. So yeah, this really is just a bit inconvenient. So that's how this YPbPr comes about here. And they do actually explain how these two are related. So our Y signal, they've got this formula here, but notice that it is actually the same as this. So the Y for YPbPr is actually the same as this Y up here. But the color difference signals are actually scaled. So 0.564 for the B minus Y and 0.713 for the R minus Y. Now if you do the math, what you'll find is that you then end up with 700 millivolts. So that's really what YPbPr is doing. It's scaling this hypothetical component video to something which is a bit more convenient for actually digitizing and transmitting on the wire and what have you. Now, as if that wasn't all annoying and confusing enough, of course there are different types of component video. Now the most common variety is this EBU N10, and this does cover PAL and NTSC, with the exception of NTSC Betacam machines, which seem to have a slightly different range here. So we notice that instead of 700 millivolts peak to peak, we've got 933. Now this is probably an important thing to note if you are working with these machines, is that you definitely need to be set up with the appropriate levels, because you're going to end up with your color saturation completely incorrect. And there's an obscure variation here. So we have the NTSC Betacam Japan. Now this is going to be for the NTSC-J standard, so NTSC-J. It's going to be incorporating the differences in that particular system, which I'll just take a moment to explain. So you'll notice here this says that the setup is 0 volts, whereas we normally have a 53.37. So this is actually a page out of N10. So the setup would basically look like this. So rather than having the black level at the blanking level, as you would have for PAL, instead you have this ridiculous offset in here. So this blue line here is the black level, and this this space under here is basically just wasted dynamic range. It never gets used for anything. And your black level is now this line here, whereas for Japanese NTSC, the black level is the same as the blanking level, so you have the full dynamic range. So yeah, that's what the deal with that is. I've put together a diagram here which shows how component video is likely to be used in a professional environment. Now, I'm not being specific about what kind of professional environment, but it could be one that transmits the content it produces on air, or it could be one that sells it on VHS tape. It doesn't really matter. The reasons for using component video are likely to be the same. Now, before we get too into it, let's take a minute to just talk about the actual terminology used here. Now, I did say previously that YUV is sometimes used to describe these types of component videos, but really this is not a very good term, because the U and V, which are color difference signals, which are very similar to PB and PR, they are actually calculated differently, they're weighted differently, so it's not equivalent. And NTSC has its own system, YIQ, which has different weightings once again, so yeah, that's why it's not a good idea to mix and match these, because so they do mean different things. Now in this context, YPbPr will be referring to analog component video, and YCbCr would be referring to SDI. It could be referring to something else, but we'll say SDI for this particular example. Now, back in the previous video, we opened with a clip from a large YouTube channel which made the assertion that PAL and NTSC were used for DVD. Now, you guys, of course, all know that that's not correct. Now, DVD actually exists in this domain here, which is component separated, YCbCr. However, he does have a point here, which is that these terms are regularly misused to talk about things in this domain which might be converted to something in this domain. So, for example, a 625 line component separated source is often referred to as being PAL, and a 525 line is often referred to as being NTSC, even though that 625 line source could actually be converted to CCAM, and our 525 line could be converted to PAL-M, which of course would have a completely different meaning. Now, despite most of the page being taken up by component infrastructure, for an entity actually transmitting their content on air back in the analog days, most of their infrastructure is actually going to be composite. And the reason for this is twofold. Now, number one, composite, of course, is the thing that they actually transmit. That's what we receive. That's what they have to produce. So, yeah, you're going to find a lot of it. And secondly, television broadcasting is a very thrifty business. Now, they're never going to spend any more money than they absolutely have to. And composite is just much cheaper to handle than component video, because you've only got one connection, whereas you have 3 connections all around of your component domain. So realistically, they're going to convert from components into PAL or NTSC as soon as they possibly can. So there's going to be a considerable amount of infrastructure along this composite line. Now, back in video number 17, we talked about sound and sinks, which is just one of the many, many, many things that gets attached along the transmission chains in the composite domain. Whereas for our VHS producing entity, well, they probably won't actually have very much composite infrastructure. In fact, they may not have any at all if they are feeding their machines with S-video. But anyway, I digress. Let's get back to the actual core topic here, which is why component video is used. So in this scenario, I've got 3 component sources. So we've got our camera, which probably will have a composite output, but a fully professional camera is always going to have component. And we've got some component video tape machines here as well. So Betacam and M2 are a couple of examples of machines which are component separated. Now, it's worth noting that other popular formats like Ampex are composite, so this does not apply. And we've also just got our test signal generator here, our color bar generator. You'll always find one of those in this environment. And of course some kind of switching, and a matrix switch for component. Of course, it's going to be ridiculously expensive because it's got 3 channels for everything. But the main reason that you have component separation is to do effects, specifically chrominance keying and any other insertion of various other graphics and what have you in the video. It's really just much, much easier to do when you have everything component separated. And that's really the main reason that we have it. If you're not doing stuff like this, then you kind of don't really need it. Even vision mixing, we don't really need to have component separation for. Now, back in the video number 19, we showed how we can actually mix composite video signals together just fine. Now, another question that I have seen asked, and I've even asked this myself at one point, is does S-video ever get used in this fully professional component separated environment? And the answer is probably not, because if we look at the actual use cases for it here, S-video basically, it doesn't really do anything useful. Our main need for having component separation is this effects kind of function here. But that wants everything to be fully separated, whereas just a YC separation is not actually all that useful, because you have to run it through either a PAL or NTSC decoder and actually to get it fully separated. And a decoder which is going to do this to the appropriate level of quality is going to be extremely expensive. So yeah, that's really just kind of pointless actually, whereas over here all we have to do is just run an extra 1 or 2 cables to have full component separation, and actually this is way cheaper than encoding things to one of these standards and then decoding them and re-encoding them. It just doesn't really make any sense. So yeah, that's why you won't really find S-video in a fully professional environment, but of course you might find it in some very specific scenarios, and I've given an example here, and yeah, do let me know if you know of any others. Now for our first practical demonstration today, we have two pieces of equipment. Starting off with this Tektronix TSG300. Now this is actually a viewer donation, and of course your donations are always appreciated, and this one in particular because this is actually a component generator. I have lots and lots and lots of test pattern generators here, but this is actually the only component generator that I presently have, so this is quite handy to have. Now, there is actually an interesting note on here. There's a sticker that says this was property of ProBell Limited in Reading. So ProBell is a company that used to exist here in the UK, and they made various apparatus room analog video equipment, predominantly switching and routing equipment, but various other items as well. Not much of it surviving, sadly, but maybe we'll see some of it here on the channel in future. Now there is another note here that it says for indication only, and this, I would presume this would be indicating that whoever stuck that to this piece of equipment does not want to find that this thing has grown legs and found its way to the factory floor, because such an item would be subject to significantly more stringent calibration and testing standards. Now the other item we have here is the PM5638. I think we saw this one once before. This is this item here, the PAL coder that sits between the components and composite domain. Now converting from component to PAL or NTSC in a broadcast environment is not a trivial matter. There's going to be some serious piece of equipment like this that's going to be doing it. Very high performance, and this thing has got a whole lot of adjustments inside of it as well, and this thing would have been regularly checked to make sure it was actually all in spec and all of that, and it's got various other bells and whistles in it, like it actually has a built-in test pattern generator and outputs on the back so you can check it against various references and stuff, all sorts of stuff. Now we're not going to get into that too much today, but anyway, these are what we're going to do for our first demonstration, where we're just going to actually have a look at the actual signals on the oscilloscope. Right, so we got these two up and running, and our setup here is exactly as we would expect. We've got the YPbPr outputs from the Tektronix generator hooked up to the Philips coder into the component inputs. Now both of these generators refer to YPbPr as YRY-BY, which is not the typical terminology, but maybe that was a more common way of describing it back when these were designed, and these are both from the 1980s. Now from there onwards we're looping out the components video signals into the oscilloscope and terminating 75 ohms on there, whereas you would normally terminate 75 ohms on there. Now this white cable here is going off to my video capture device, and that's basically how you're seeing the preview on screen. Now that device does actually have a component input, but even I am a bit too cheap to run 3 cables across the room, so yeah, that's what we're using there. Now if we have a look on the oscilloscope here, we can see all of the signals. So we can see the yellow trace here, that's the composite output of our Philips coder here, and these ones are the 3 component signal inputs. Now just looking on the oscilloscope here, we can immediately see some interesting things which we may not otherwise know. So for example, if we have a look at the green trace here, which is the luminance, we can see that there is actually a sync signal present on it, which is what we would expect, but maybe there may not be one. There is some obscure scenarios where it could be missing. The other thing that we can see is that our range here, if we do a delta on the blue channel, we can see that it's exactly 700 millivolts as we would expect, and this means that this generator is set up to generate an EBU N10 style outputs. Now, as I said, there are other possibilities, so that's always something worth checking, especially in this case because I've never actually seen the manual for this Tektronix generator, and that's very unusual. Now, normally Tektronix people are really on it when it comes to scanning their manuals, but yeah, this one doesn't seem to have been digitized yet, so if you have a copy of it, let me know about it. Now the other thing that we can learn from looking at these traces is how this PAL coder is actually set up. So if we look at our color bars here, now notice that our color subcarrier is actually going way above. Let me just expand it a bit. It's going significantly above the white level. So this is what you would typically see with a 100% bars, and what this indicates is that our PAL coder accepts a 700 millivolt range input, so it expects 700 millivolts to be 100%, and obviously 75% bars would be a lower voltage. So everything here is exactly what we would expect, and yeah, all looking very nice. So yeah, let's just run through the various test signals that this Tektronix can actually generate and have a look what they all look like. For our last demonstration today, I thought it would be interesting to have a look at the various different types of component video on the oscilloscope. Now for this, we've got out our trusty PT5300 again, and from memory, I think this is actually the first time we've gotten it out since the dedicated video about it. That was video number 10. Now what we're looking at on the oscilloscope here is the PT5300 combination test card, because it's just fun to look at on the scope, no other reason for using that. Now this is a normally digital only item, however we've actually got this fairly budget SDI to analog converter box out here so that we can actually put them on the scope and see what's going on. And this does have some dip switches on the side of it which allow us to set the various modes. On the back we have a legend describing the various dip switches. In particular we're interested in switches 7 and 6. Now 6 is going to be the SMPTE versus Betacam, and that's of course this thing we were talking about earlier here. And the 7 is going to be this, back once again on this piece of paper, this offset here, the setup 53.3 or 0. But they've actually described it as 7.5 IRE or 0 IRE. And the IRE from memory, that stands for Institute of Radio Engineers. This is an abstract way of describing the scale between the blanking level and the white level. So 0 IRE would be the blanking level, and 100 IRE would be the white level. So if you set this for 7.5, then that means you've thrown away 7.5% of your dynamic range, and I believe that is actually standard for NTSC. Now what we should find is that these switches, this one here should only do anything in the Betacam mode. I'm not expecting it to do anything in the this mode here, SMPTE levels, but it'd be interesting to try it out and actually see what it does, because I've never actually played with those switches before. Now for this demonstration, unfortunately we have to wave goodbye to our nice measurement quality signals that we were getting out of the Tektronix. If we have a look at the N10 specification here, the luminance is supposed to be having the blank level at 0 volts, and the different signals are supposed to be centered on 0 volts. But if you look on the oscilloscope here, everything has this nasty DC offset. So for the R minus Y, there's the 0 volts down there, so it's all the way up there, and our luminance, once again, it's all completely positive, so yeah, that's not ideal. Now if you're working for Tektronix and you produce something with an output like this, you would have been set alight, but you probably will normally get away with it, provided that nobody's looking too closely because of input clamping on the various things that this was probably going to be plugged into. But anyway, we'll pretend we didn't see that and actually get on with the actual demonstration here rather than getting distracted over pedantic details which don't really matter anymore. Now first of all we'll have a look at the Betacam versus non-Betacam switch, so that was number 6. I've got a suitable implement here, and I'm hoping this thing is just gonna work without me having to power cycle it. Let's get that in there. So switch that up. Oh, yep, there we go. So everything went up in amplitude, so all the different signals and the luminance do change. That's what we would expect. Now the other test I wanted to do is whether or not switch 7 does anything in SMTPE mode, which it shouldn't. Nope, nothing, no change. There's some flickering there, but yeah, it's not doing anything. So we go back to Betacam mode now and switch that on. Oh, hang on a minute, what's that done? Nothing now. Oh dear, it's not responding to that switch anymore. Have I confused it? Let's power cycle it. There we go. I just upset it a bit too much there. So right, we're back in Betacam mode. Is this going to do anything? I think it is actually. There we go. So when I switch it up, if you look at the luminance there, so we can see the offset. Actually, let me just make this a bit bigger so we can
And I'll turn the color difference signals off because they're not actually helping us very much right now. So if we look at just the luminance by itself and fiddle with that switch, you can see, yeah, look, so the black level, that's the black level in the normal NTSC or NTSC mode. This is just 525 line. There's no actual NTSC here, but that's a normal black level. But if I switch it to the Japanese mode, it goes down like that. So there you go. There you have it. There's the various different modes.
Well, that's all for this video, and I have to say that I'm really enjoying that we're getting some people with some really good expertise watching these videos and actually commenting and contributing. So if you know anything that I've missed out here, or maybe you've spotted something that I said that wasn't quite correct, let me know in the comments. Now, the other thing that I had to leave out of this video is talking about the very early years of component video, where there was all sorts of different standards and permutations and what have you. Now, I've had a bit of trouble actually finding any relevant documentation to talk about that really early stuff in a way that's probably going to be factually correct. So if you know anything, of course, let me know in the comment section. But anyway, that is all for today's video. Thanks for watching.